Hi, I'm Ben-Yaakov. This presentation is entitled Introduction to Motor Drive Control, and this is a part 2 of an ongoing seminar. It's an English version of an in-house seminar given at IRP Systems, Ness Ziona, Israel. Please watch first the part 1 because I am now relying on part 1, although I'll give a short sort of a rehearsal of the subject, some of the subject of part 1. So we talked about in part 1 about stability, and we talked about the Nyquist criteria, which is based on the fact that you can recognize whether you have poles in the right half plane of the complex plane by looking at the amplitude of the loop gain and watching the difference or the phase margin, that is how close you are to 180 degree. And if you are not reaching 180 degree, then the system will be stable. However, if the phase margin is small, then you'll expect to see overshoot and ringing for a step excitation. And in the frequency domain, you'll see sort of a hump here, sort of like a second order system. And this overshoot here and this hump are a function of the phase margin. The smaller the phase margin, the larger will be the disturbance. So therefore, you'd like to keep in the design the phase margin in the order of, say, 45 degree. A too large phase margin is not good, because then you'll have a narrower bandwidth. Now, we talked about minimum phase system, that I'm actually dealing only with these systems in this presentation here. And in this case, we are talking about a system in which we do not have a right half plane zero, because in this case, things are getting a little bit messed up. If you have a right half plane zero, it means that you have a behavior of a zero, but rather than having a phase advance of 90 degrees, in the case of a right half plane zero, you'll have a lag of 90 degrees. So you're actually adding another lag, and therefore you have to take it into account in the Nyquist criteria, which I'm not doing in this presentation. And we also found that what is important, really, in the case of a minimum phase system, is the rate of closure. That is how the loop gain is actually approaching the 0 dB. And I've shown that if it is approaching with a closure rate of 20 dB per decade, then we are in good shape, because it would imply that this area here, or this range here, is actually controlled by one pole, and then therefore one pole would have a maximum of 90 degrees. And this is because if you have a situation of poles and zero, etc., and then all the poles and zero actually cancel out when you approach this curve, and because once you have here 20 dB per decade, it would imply that all the poles and zero, actually all the phase shifts canceled out, and you are left with the 20 dB per decade, which implies a maximum of 90 degree phase shift. And then I've shown the method of 1 over beta, and the idea is the following. If we'd like to get the loop gain from two parts of the system, say forward and the feedback part, or two in tandem and then feedback of one, then we can do it two ways. One is to take one part, multiply it by the other, and get the loop gain. And then if you like to change this part here, which would be a controller, then you have to do it again. So this is not very convenient, and what I've shown here is that if you have, say, the plant, and then you like to design a controller or examine a controller, then what you'd like to do is actually plot it in 1 over. And if you do that, then it turns out that this distance here is actually the loop gain. And then this point is the critical point that you are looking for, and this is the point where the loop gain is equal to 1, because A is equal to 1 over beta, so BA is equal to 1. And therefore, this is the area you'd like to look at, and from the rate of closure here, you can tell as to whether the system is stable, or in another word, you can then design a controller such that the rate of closure will be the 20 dB per decade. And then I've shown here that this is again the rate of closure, although it is sort of plotted differently. It's not a product, but just a difference here. And also, if then you have a system like this, this is the A part and this is 1 over B part, then here are several situations of crossover situation or frequencies. Here we have 1 over beta that goes up 20 degrees, and so this system also will be stable because you have a rate of closure of 20 dB. Here we are exactly at the pole, this second pole here, and therefore the phase margin will be 45, the 90 from here plus the 45 here. And then we have a case again of going down 20, and then this is flat, so we have again a rate of 20 dB, here again 45, and here, which is nice, if we have it going down minus 40 dB, and if you manage to get a 1 over beta that goes down at 20 dB per decade, so actually the B itself is going up at 20 dB per decade, then the rate of closure here is 20 dB per decade, and this is okay. In this case, if we are at the pole at the breakover frequency, we'll have a 45 degree. So this is something that I've already discussed in part 1 of this sequence, so you're welcome to. So let's go back now to the issue of controlling a motor. We have here a motor, here is an inverter, this is a PWM feeding the inverter. We have then a controller with some algorithm, some phase compensation actually, and then we have here a sum which is comparing in this case, I'm supposing that I have a signal of the speed, comparing it to the required speed, and here we have a sort of a feedback system. So let's now have a look a little bit inside what we get here in the system itself. What are the blocks here? This is of course very simplified here. So let's start with the motor itself. The motor, here I'm showing a brushless DC motor in a star connection. These are the phases, and here is actually the equivalent of the inverter. This is the source feeding the motor. Now I can actually separate here, I'm sort of shown here, also is a star, so due to symmetry, this point and this point are the same, so I can have a look now at one of the phases here. And in here what I see the input, I see a resistance, which I'm not showing here. There is a resistance to the coils here, then the inductance, and this is the back EMF, which I'm not showing here. There is a back EMF of the motor, which is a function of the speed. So basically what we have here for one of these phases, we have a input voltage, a impedance, and then a back EMF, which is some constant times the speed of the motor, the angular velocity. And we can represent this circuit as a sort of a block diagram of this nature, and let me explain what's the steps to get it. First, we're saying that the voltage across the impedance is the difference between Vin minus the back EMF. Vin minus back EMF, that's the voltage, divided by the impedance is the current. So this will be the current. So looking at this, we can represent it in the following way. This is a difference, or here a summing junction with plus and minus here. This is V in, and this is now the feedback. Omega times kV. kV is the constant relating the speed of the motor to the back EMF. And then divided by the impedance here, which I'm showing here as R plus SL. And this is now, the output is the current of this. So this is sort of a block diagram representation of this circuit or this network here. Now let's move now to the mechanical portion. This represents the moment of inertia to which the motor is exposed to, and this is a outside mechanical torque. Now, if we have a moment of inertia and we have a total torque which is imposed on it, then we are going to have in the mechanical framework a force which is the moment of inertia times the acceleration, which is the derivative here. And then I'm adding to it a portion which is friction. Actually, friction is normally non-linear. We have higher order components like omega to the square, but just as a first approximation to simplify things here, I'm assuming that the friction is a function of the speed and then times some constant. Now, this is exposed to the total torque, which is the electrical torque coming from the electrical part, and minus the mechanical torque, which is loading the motor. Okay, so this is the net torque on the moment of inertia. This is the force plus the force due to the friction, and then doing some arrangement here, I'm getting this relationship, which means that the speed of the motor, I've just taken the Laplace variable as a derivative here, and then I'm finding that the net torque divided by this pole here is the velocity or speed of the motor. And therefore I can also represent this as a block diagram. Here is a difference, so here is a summing junction, and this is the mechanical time constant, you might say, of the motor. This is the moment of inertia, and this is there's a missing B here, I'm sorry. Okay, this should be the, you can take out B outside the parentheses, which I didn't do here. So now we can combine the two parts, this electrical part and mechanical part of the motor, and get this block diagram which represents just the motor itself. This is the summing point for the voltages across the impedance. Here we're generating the torque, and then we impose the difference here on the moment of inertia, which is producing the speed of the motor, the angular velocity. Here we have the constant relating the speed velocity to the voltage, which is then subtracted here in the input circuit. Now this, of course, looks like a feedback system. Here is one part and this is the other part, the beta. And so the A open loop is this part, and beta, of course, is kV. And we know that the transfer function between input and output is according to the classical feedback equation. And therefore, we can now write it down. This is now the motor itself. Now, this is not an external feedback. Let me just clarify this. This is within the motor, representing the fact that on this impedance you have a difference of voltages, and this is what this junction here, summing junction, and this line are actually representing. So to get the block of the motor itself, we need to get V into omega, and therefore here it is, and just opening it up, I'm getting this relationship, and I see that I have here a second order system in the Laplace domain, and which can be, it turns out to be real poles, can be broken. Anyhow, this could be also a complex pole, of course, broken into two poles here, and so we have a system with two poles, assuming it's a first order, then we have this picture here. So this is the block of the motor itself between V in and omega. V in produces the torque produces through the mass the speed. We have here two poles. This at a lower frequency usually will be due to the moment of inertia, and this will be at a higher frequency due to the electrical network, R and L, and this will be therefore the transfer function of the motor itself. Let me clarify, however, a couple of things here so we can better understand what we are talking about. Now, this transfer function is small signal transfer function. It is assuming, by the way, which I didn't say, we are assuming that this is constant. This is not changing due to this excitation. In reality, it could be. It could be like the vehicle is moving. So we neglect this, so we assume this is constant. And so under these conditions, we are talking about a small signal excitation, and the resulting small signal changes in the velocity. Now, the actual excitation of the motor is via an inverter. Now, this inverter usually three-phase bridge, and we are producing an average, say, sinusoidal waveform, and this sinusoidal waveform is actually produced by a duty cycle of the switches going up and down, and so that the average value here is this voltage fed to the motor. Now, when we are talking about excitation or the small signal response here it is, the small signal response, we are talking about modulating this signal so that here it is. This is now the signal or the drive to the motor, the average drive to the motor, and now we are actually modulating it with a small signal. This is this frequency here. If the modulation is at a low frequency, then we are going to see here an envelope here. If the modulation is at a high frequency, that's what we are going to see. So this is a modulation above the frequency that is fed to the motor associated with the rotating field or magnetic field within the motor. Now, you are limited by the modulation frequency of the inverter. That is, the inverter has a basic switching frequency, and therefore, according to the Nyquist sampling criteria, you cannot produce with this sort of sampling system a frequency which is higher than half the switching frequency. So therefore, depending on the modulation frequency of the inverter, the frequencies above half this modulation frequency are meaningless. So this is something to bear in mind, that you cannot handle frequencies which are beyond half the sampling, or in this case the switching frequency. And in fact, you do have to put some analog filters in order to cut out all these frequencies above this in order not to get folding or aliasing signal. If we just want to stabilize the speed of the motor, then we need now a feedback loop that will be fed from a signal that we want the speed to follow it. This is a sensor for the speed. K omega is just a sensor for the speed. And this is the motor itself. As I've said, this is not actually an external feedback. This is just representing the internal back EMF imposed on the impedance. So in order to stabilize this system and to get the dynamic response you want, we need a controller here. And then we have now a closed loop system in which we have one part here and this one part here. This is a beta, and this is sort of the new open loop with this controller. And our task now is to come up with a controller that will ensure stability and also the bandwidth that we want. That is the response time that we want. Now, we have to take into account that in fact we have not just a controller, we have also the inverter. The inverter itself has a transfer function, the modulator and the inverter itself. In this part, part 2, I'm not going to get into this detail, but just to mention that this is given and this is something that we have to come up with. So let's call this whole block the compensator, including the inverter and the modulator. This is now the motor, and this is now the outside feedback, just a constant. This could be also frequency dependent, but let's assume it's frequency independent. This is the loop gain, because the loop gain now is this part times this times this. So I'm taking this as given, here it is, and this is something that we have to come up with. So here is the part which is given. This is not Ki, this actually should be times K omega also, because we have it also this part, but let's assume that this is then given. And now we have to come up with a compensator here to close the loop properly. And here we see that we can do it two ways. We can do it with a 1 over compensator, 1 over B as I called it earlier, that looks like that. Or I can have one which looks like that. This is now a 20 dB per decade going up the 1 over, while this goes down by minus 40, so the rate of closure is 20 dB, and same thing for here. A classical way to design a compensator is based on the so-called PID controller. That is to have this one, B itself, not 1 over, as a PID controller. And PID means that you have actually a summation of 3 parts. One is the proportional, one's the integral with its own coefficient. This is coefficient for the proportional, and it's divided by S means that it's an integral, and you may have a differential also part. So this is proportional, integral, and differential, and here we have the S for the derivative operation. If I sum these up and I sort of combine them, I get this transfer function. The second order in the numerator divided by S, and of course I can take out the zeros here from this second order equation by solving the second order polynomial. Now, there's another way of looking at it, and this is the following way. If I have a sum of these 3 components, looking at it in the frequency domain, the Kp is a straight line. The integral is this line here, and the cross here at 0 dB is when this is equal to 1, this is 0 dB, it should be 1, and therefore the angular frequency is equal to Ki, here it is, and therefore the frequency is Ki over 2 pi. So this is the crossover frequency of this curve here, this integral part, and obviously it's a function of k. The larger the k, this will move back and forth. And then for the derivative, I do the same thing. I'm saying that this is a derivative, looks like this, and the crossover point is when this is equal to 1, or that the frequency is 1 over 2 pi kd, so here is the frequency here. Okay, so I have a summation of 3 curves, 1, 2, and 3. In this region here, this one is much larger than this, so it's approximately this thing here. In this region, this line is much larger, or this value here, much larger than this and this, so therefore I'm getting this straight line. And here, of course, this part here is larger than this, and naturally larger than this, and I get this black thing. This is an asymptotic approximation of the curve itself, and this is in fact the PID compensator. Okay, we have here like a bucket here, and this is the integral part, this is the proportional, and this is the derivative. And now, in using the method that I've shown before, you can use this for controlling the or closing the loop. Let me just mention here that I've added here some broken line to say that in reality these will not go to infinity, and this also will not go to infinity gain. Rather, at one point there is a limitation here of the gain that you can get both in the analog or digital domain, and same thing goes here. You cannot get very, very high gains at very, very high frequencies, so eventually this is sort of going down. So the portion that we can use is this portion here, which is physically possible. So this is now the PID. I'm sorry, this should be the same slope here. And this is now 1 over PID. Okay, so this is now using the method that I've shown before, can now be used, this one here, of course depending on the constant. You can put various constants here to move it around. So you can use it like this to get a closure here, or you can use it here to get a closure here, or you can get it here to get a closure at much higher frequency, utilizing the fact that here you have in fact in the PID a phase advance, which is sort of compensating the extra phase lag that you have in the system. So therefore you get a nice rate of closure of 20 dB per decade, which means that the system will be stable, and of course in this case the bandwidth will be much, much larger in a system. One way is to use a high order compensator. Another way is to try to reduce the order of the system. That is, rather than dealing with a system which is a second order, as we have it here, due to the fact that we have the mechanical and electrical part, there is a way to sort of modify the transfer function, the inner transfer function, by an extra feedback, an extra inner feedback here, an inner feedback in the loop. So here I'm taking a measure of the current, feeding into a junction here, a summation junction, and then there is another compensator for the current. So what is the idea behind this, and what could it do? So let's assume that I have a system like this. Let's assume the voltage here, which is the back EMF, as a matter of fact. Let's assume that we're at a given point and the back EMF is about constant, okay? So in this case, we have here sort of a 0 in terms of small signal. We are measuring the current. We are comparing it to a reference. So in this system, in a closed loop, we are going to have this function here. This is this part here. The feedback here is 1 divided by this. So when the loop gain is much, much larger than 1, this is something that I've discussed in the first part, or when the loop gain is larger than 1, this converges to a gain of 1. So what does it mean? It means that this part, which originally was an inductor, now becomes like a constant between here and the current because of the feedback. So we have kind of dropped the effect of the inductance. Of course, this would be correct for the range in which this loop gain is larger than 1. So therefore, if this is now the pole due to the electrical part, and if we have an inner loop that sort of drops out the inductor and makes the current output proportional to the command here, then rather than having a break here, we're going to have a continuation of the 20 dB per decade. So therefore, the compensator could be much simpler. It could be just the portion, let me subtract this portion here, which is a PI. We are not using the derivative part of the PID. And this is, of course, a much simpler. We don't like to use the derivative part. Let me just go back here. This derivative part means that you have a high gain at high frequencies, and not only that it's difficult to sort of realize, but also it sort of amplifies noise that you have at a high frequency. So therefore, we really don't like very much the derivative part. And here it's nicer. So if we can modify the transfer function by the inner current loop, that's what it is, this is the inner current loop, then therefore we'll sort of reduce the order of this system. Rather than having 2 breakpoints, we're going to have only 1 breakpoint, but this one is been eliminated. So this is going to be discussed in the third part of this sequence. And at this point, I'd like to thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.